In this video, we're going to look at an example of graphing a polar equation and show some of the steps that you might use to do this on your own. Let's consider the equation r equals 5 sine of 2 theta. You could graph this polar equation using a couple of techniques. If you like remembering formulas, you might recall that this is going to be the graph of a rose. And because of the 2 theta, it's going to be a graph of a rose with 4 petals. I want to go through the process, through the construction of creating this graph for us, though. To do so, let's graph r equals 5 sine of 2 theta, first in the theta r plane. Recall this is a sine function with a period given by 2 pi divided by b, or in this case, 2 pi divided by 2. And so this is a sine function whose period is pi. So we'll see one entire cycle on the interval 0 to 2 pi. It's a sine function that would normally start off at the origin and end at pi with an amplitude of 5. And so our sine function would probably look something like this. Recall, we can use this graph to describe the length of a radius vector for any value of theta. A couple important values of theta are where our graph crosses the theta axis, which we know is at 0 radians, pi over 2, and pi. And so at these angles, our radius would have a length of 0. Now, well, at 0 radians, we'd be talking about this direction. So in this direction, our radius would be a 0. At pi over 2, we'd be up here in this direction. Also have a radius of 0. At pi, in this direction, we'd have a radius of 0. And if we consider a little bit more of our graph, we know that it would go on. Our next value would be right here at 3 pi over 2. So at 3 pi over 2, down here, our radius would be 0. And then it would again occur later in our graph when it came back up. Well, this would be at pi, 2 pi. And so over here at 2 pi, we'd be at a radius of 0 again. For any other value of theta, we would have a non-zero radius vector that we could plot in our polar coordinate system. Let's first consider values of theta that live in this first quadrant. Thetas that go between 0 and pi over 2. For these values of theta between 0 and pi over 2, our radius vectors would always be positive. From 0, they would get longer and longer and longer till eventually they're the longest at pi over 4. And so at an angle of pi over 4, which would be in this direction, our radius will be the longest. After pi over 4, our radius vectors will start getting shorter again till eventually hitting a length of 0 at pi over 2. So if we consider graphing our polar equation in this quadrant, it would start off at a radius of 0. It would get longer and longer and longer until eventually it'd be longest at pi over 4. After pi over 4, the radius would get shorter until eventually being 0 when we get to pi over 2. As we rotate from pi over 2 to pi in the second quadrant. From pi over 2 to pi, our radius vectors would always be negative. They would be the longest negative at 3 pi over 4, in which case the radius would be negative 5. So as we rotate from pi over 2 to pi, and rotate through the angle of 3 pi over 4. Let's put 3 pi over 4 up here so it's not in the way. 3 pi over 4. Our radius is getting longer, but in the negative direction. So as you rotate through the second quadrant, our graph will be reflected into the fourth quadrant. They'd be longest at 3 pi over 4, where they'd be negative 5. So they'd be about out here. And so as we rotate through this quadrant, our radius will be getting longer and longer and longer, being longest at 3 pi over 4. They'd still be negative, but getting shorter as they approach pi. And so it looks something like that. After pi, as you rotate through this third quadrant towards 3 pi over 2, then our graph would be, well, the radiuses would be given by our values on this function. From pi to 3 pi over 2, our radiuses would always be positive. So as you go from pi to 3 pi over 2, our graph would live in this third quadrant. They would be the longest positive right here, which is going to be at, now where is this at? This is at, was it 5 pi over 4? And so at 5 pi over 4, this is when our radius would be the longest. So when we constructed our graph, as you go through this third quadrant, you'd start off at pi with a length of 0, so at the origin, and your radius would get longer and longer, eventually being longest at 5 pi over 4. After 5 pi over 4, they'd still be positive, but getting smaller again, until eventually being 0 once you got to 3 pi over 2. After 3 pi over 2, as you rotate through this fourth quadrant towards 2 pi. As you go from 3 pi over 2 to 2 pi, our radiuses are always going to be negative. So our graph won't live in this fourth quadrant. They'd be reflected back over the origin to the second quadrant. They would be the longest negative right here at 7 pi over 4. And 7 pi over 4 would be this direction this way. 7 pi over 4. But since it's negative, it'll be longest in the negative direction, or around the origin, in the second quadrant at 3 pi over 4. And so our graph, as you rotate from 3 pi over 2, the radius would be negative, or at 3 pi over 2, the radius would be 0, so you'd be at the origin. Your radius would get longer and longer and longer, eventually being longest at 7 pi over 4 in the negative direction, and then start getting shorter and shorter and shorter until you eventually have a radius of 0 at 2 pi. Well, I hope this video is helpful. This does give you an example of how you'll graph the rows on the interval 0 to 2 pi. I hope this is helpful, and I'll see you next time.